All right, it's time for some 4.3, solving for real and imaginary zeros of polynomials. This is actually a two-part lesson here. We're going to have some application later on, but for now, let's get started with a little bit of warm-up, okay? We want to solve for k, given that x plus 2 is a factor of f of x, okay? So if x plus 2 is a factor, what does that tell us? What do we know? Well, if I were to divide out x plus 2 from that polynomial function, I'd have a remainder of 0, right? Because it is a factor. So I could do negative 2 in my synthetic division, or I could substitute negative 2 and have 0 for my output value, right? It'd be 0 for my remainder with synthetic division, or 0 for my output when I substitute in negative 2. Due to the k's being in this function here, those constants, what I'm going to do is I'm going to use direct substitution because it's going to be easier to deal with than doing synthetic division. All right, so if I were to plug in negative 2, substitute negative 2, I'd have 0 be my function value. So I'll just go ahead and set this equal to 0 based on what I know here. And let's see here, plus k. Lovely. All right, we can do a little algebra here. We got 16 here. This is gonna be a negative 8, but then it's positive 8k because the subtraction right before that. Then I have negative 2 squared, which is positive 4k minus 1. So I'm going to combine some like terms. I'm going to bring this up over here. And I'm going to have 0 equals be 15 plus 12k. So I'll subtract 15 and then divide by 12. So I get k equals negative 15 over 12. That would be, they're both divisible by 3, so I'd get negative 5 over 4. Woo-woo. Awesome. So there's my k value for that one. We used what we knew about x plus 2 being a factor to help us solve this problem, right? That's where we started this one. All right, write the equation of the polynomial. I'm going to zoom in just a little bit over here. So, well, I need to identify where it's either touching or crossing the x-axis. So it'd be at negative 1, looks like at positive 2, and then positive 4. It's just touching at negative 1, right? And bouncing off that. And then at 2, though, it like flattens out. So what's actually happening there is it's going to be to the third power because it's not directly going through like it is on 4. So it's still an odd exponent there, an odd power because it's going through it, but it flattens, so that becomes that power of 3. Wonderful. So let's see here. We got our factors, and I'm going to throw an f of x, and it looks like this is going to be a negative function, right? And it's going to be an even power overall because they're both going down. I'm basing it on the end behavior there. Okay, so I'd have x plus 1, and that's squared because it's bouncing. Then I have x minus 2, and that's to the third power we said. And then we have x minus 4. All right, so that looks good so far, but there is something that we're really not including here is we might have that coefficient a. So I'm just going to toss an a out in front. And the way that this will work is when we do solve for this a, the negative sign will work its way out in this, okay? Well, what can I do to figure out what that a, that lead coefficient, is going to be? I could take another known point. In this case, it looks like we got our y-intercept at negative 4, and I can plug that point in, which is 0, negative 4. So if I substitute in 0 for my y value, or sorry, 0 for my x value and negative 4 for my y, I can solve for a. And I'm going to do that right now. I'm going to try and keep this video a little bit less, so I'm going to pause. So after we substitute in, we end up with 32 on the right-hand side. So if I divide by 32, I'm going to get a equals negative 1 over 8. So that means my final answer here is, I want to change colors, we got a lot of red going on. I'd have f of x equals negative 1/8. See how the negative worked its way out there, which makes sense for this function. And then I have x plus 1 squared, x minus 2 cubed, x minus 4. It just makes it in there. Woo-woo. There is my wonderful, beautiful function there. in factored form. If it asked us to put it in standard form, we would just end the day, because nobody wants to do this for a degree of 6. Oh, no, thank you. All right, we're moving on. All right, we got the fundamental theorem of algebra here. So it states that if p of x is a polynomial of degree n is greater than or equal to 1, so it could be a degree of 1, 2, whatever, then p of x equals 0 has exactly n roots, including the multiple and the complex roots. So basically what this says, guys, if it's a degree of 1, it's got 1 root. If it's a degree of 2, it's got 2 roots. If it's got a degree of 3, so on and so forth, right? To the nth degree, polynomial will have n roots. All right? Wonderful. And we count those double roots, a multiplicity of 2, as 2 solutions, triple as 3, so on and so forth. So that's why this particular problem up here, which was a degree of 6 overall, had 6 solutions. We had 2 for the first one, 3 for this one, making 5, and then 6 total. Okay? Wonderful. One thing that I think has been overlooked in many classes is that complex roots also include real roots. We often use the word imaginary and complex, very interchangeable. That is not the case, okay? So complex roots also include our real roots. Think about it. With this statement down here, which spells it out, complex roots are a plus bi, where a and b are real numbers. So if b was 0, away goes that imaginary term, and we're just left with a, which is a real number, okay? So complex has the real and the imaginaries included. A couple of theorems here. Love me some theorems. So we've got, if a plus bi is a 0 of a function, then a minus bi is also a 0, okay? So that is our complex conjugate pairs, and then it also works with radicals. So radical conjugate pairs theorem is if we have 2 minus root 3 is a 0 of a function, then 2 plus root 3. Think about the quadratic formula, right? It's negative b plus or minus the square root. So if we have something minus a radical, we got to have something plus a radical, right? So that's why that one it's going to have those 2 solutions. Whew, we're cruising now. So let's use this conjugate pairs theorem. A polynomial of degree 5, whose coefficients are real numbers, right, has the zeros 1, 5i, and 1 plus I. Find the remaining 2 zeros. Well, if 5i is one of them, then negative 5i would be the other. And if 1 plus I is one of them, then 1 minus I would be the other. And something I didn't mention before, that this also is coming from our quadratic formula. It's just if I have a negative inside of this radical, right, then it's going to be a number plus an imaginary number and a number minus an imaginary number. So all coming from that wonderful quadratic formula that we know and love so much. So now we have another example where they're going to get lengthier and lengthier as we go. It says, let x equal 7i be a 0 of the quadratic function y equals g of x. Write the function in factored form and in standard form. Factored is always the easier one to go with, and then sometimes it does ask for standard. So I would have g of x equals, and if 7i is one of the zeros, x minus 7i would be the factor paired with that. And keep in mind, if 7i is one of the zeros, then negative 7i is the other 0. So I'd have x minus negative 7i or plus 7i. Don't forget about your basics when we're writing these functions out. It's like if you had x equals 3 was a 0, you would know that it's x minus 3 is my factor, right? So don't forget about those things just when we throw in imaginary numbers and we get scared. Those, you got to make sure that you are still gathering that information and handling it well. All right. So this is my factored form, but now we want to get it into standard form. So we're going to FOIL this out. All righty. So if I do that, I'll change colors now since we're going to go into our standard form. I'd have x times x is x squared. Then I'd have positive 7i x, and then minus 7i x, and then let's see here, that's negative 49i squared. So these are going to cancel. You're going to see that quite a bit here, and you'll see where this comes in handy. with those cancellations because it's like a difference of squares type of situation. Then I'm going to have I squared is -1, so it's going to be positive 49. Here we are in standard form. Don't forget my g of x. I love it. It's fantastic. We're having so much fun here with polynomials. If you see Officer Gregorio anytime soon, ask him what his favorite math word is. He'll say polynomials. All right, next one here. We've got if x equals 2 minus root 5 is a 0 of a quadratic function, then write that quadratic function in factor and in standard form with integer coefficients, meaning we got to have numbers, not fractions. We don't want radicals as our coefficients, integers, positive, negative numbers, right? Okay, lovely. So if 2 minus 5 is a 0, then we know that root 5. Then we know 2 plus root 5 has to be one of the zeros. So what I'm going to have here for my function, it's not named here, so look at that. We get to pick the name out. That's exciting. I'm going to have x minus 2 plus root 5, and, oops, don't forget that second parenthesis, and then x minus 2 minus root 5, because those are my two zeros, right? So I'm just taking that, boom, x minus that, x minus that. All right, we're cruising. We can't really leave it like this in factored form with all these radicals, and it's just kind of, messy here. So we're gonna clean it up actually a little bit. So what I like to do here is, I'll switch colors now for the bonus algebra, is I like to do a little bit of creative grouping here. First off, we're going to distribute that negative, so -2 minus root 5, and then here will be -2 plus root 5. Okay, so I've taken care of the inner parentheses. Now what I want to do is notice how we have an x minus 2 and an x minus 2 as something that's like in each one of these factors. What I can do is I can actually group these two and these two. And now what I see is something minus root 5 and something plus root 5. Well, isn't that like our difference of squares? And what happens in our difference of squares? The outer, this one and this one, when multiplied together, cancel out with the inner, this one and this one. So now that we've noticed this, we're going to save ourselves a ton of work when multiplying this out, because I only have to worry about the first two, and I'll get x minus 2 times x minus 2, which is x squared minus 4x plus 4. When we FOIL that out, you should be able to do that in your head by now. And then I only have to worry about the last, which is negative root 5 and positive root 5, so negative 5. So it'd be negative root 25. And then, look at that. We are in standard form with integer coefficients. All right, so we went from our factored form. This would be like this one up here. Either one of these would be acceptable for your factored form. But then multiplied out, this is our standard form here at the very end. But this trick, so to speak, being just creative with your algebra of finding these and realizing that it's a difference of squares, like when we have x minus 9 and x plus 9, it's this one and these, they end up canceling each other out, right? So that's what we noticed there, just in a more complex situation. Keep your eye out for that. It's going to come up quite a bit. Alrighty. So pay attention to the wording in this one. It's specific. All right. Find a polynomial h of degree 3 whose coefficients are real numbers and that has the roots 3 and 6 minus 4i. Let's jot this down right now. We know the other one's going to be 6 plus 4i, don't we? Okay, get that out of the way. Write the answer in such a way that each factor contains only integer coefficients. So it sounds like we can still leave it in factored form, but we can't leave i's in there, okay? Can't leave i's, can't leave radicals, can't leave fractions or anything like that. We got to have integer coefficients within the factors. So not as much work, but still a bit of work ahead of us. Okay, so let's say we got... over here, we'll go with h of x equals, and we'll have x minus 3. Then we'll have x minus 6 minus 4i, and x minus 6 plus 4i. Okay. So we're taking those roots and then getting our factors from that. So now I'm going to leave the x minus 3 off to the side for a bit, and I'm going to get going on some algebra with the other two over here, all right? So once again, over here we have a similar situation to before. I'm going to pause. So very similar to the last problem, but now what I'm going to do is, again, I'm going to group the like ones in each of these two factors because I noticed that difference of squares type of pattern that's showing up here. So now I only have to multiply the x minus 6's together and the 4i and negative 4i together because I know the inner and the outer, when FOILed, will cancel out. I don't have to worry about them, and those are the messiest ones to deal with. All right, so let's do that. So I'm going to have x minus 3 still, and then in my next one, I'm going to have x minus 6 times x minus 6, so that's x squared minus 12x plus 36, and then I'm going to have negative 16i squared. We're almost there, and I'll have x minus 3 times x squared minus 12x, and this one right here is going to become positive 16. So if I add those two together, what do I get there? 52. Wonderful. Fantastic. Excellent. I love it. That looks good to me. That looks good. So what we have here are, it's still in factored form, but I have integer coefficients. I don't have any more imaginary numbers. I don't have any roots. Nothing like, I don't have any square roots. We're all good. We're Gucci, as they say when they do math problems successfully. Alrighty. Now we're going to introduce the calculator here. So if you don't have it out already, make sure you get your TI-84 or TI-83. I'm always strapped. I've got a custom cover, YORO, hashtag YORO. You only round once for mathematical accuracy, of course. But so you can see the keystrokes that I've got going on. We've got this fancy little emulator here that I downloaded from the interwebs. So we'll see how it works. I haven't used this one yet. Hopefully it goes well. All right. So we want to find all the rational zeros using a calculator, okay? So we're going to find anything that's, you can see clearly where it crosses the x-axis. We might have to solve for those zeros using some functionality on the calculator here. We'll go over that, all right? So if you hit second trace and 0, we'll be able to find that 0. We'll go through those keystrokes in just a sec. And then we're going to use some synthetic division to divide those factors out of that function and then analyze what's left over there. And remember, it's not like we're taking them out. We're breaking it apart. Okay. So let's hop to it. We're going to plug this into your calculator. I'm going to do that while I have the video on pause. So feel free to pause it if you need. Alrighty. So we have our function plugged into the first y1. Make sure you got it plugged in correctly. That's always helpful. And then we'll hit graph. If your zoom is a little weird, maybe you use it last, something like that, you can always hit zoom, and then standard is 6, so I can hit 6 there. And then it'll bring up my 10, 10, negative 10, negative 10 window. Now, it's a little tough to see here, so I think I want to zoom in. So I'm going to click the zoom, and I'm going to hit number 2 there. So if I hit 2, it'll bring me in. I actually have to select where I'm zooming in on. I want to zoom in right there at 0, 0. That's fine. And what I can see here is that it's clearly hitting the x-axis here and here. Where that is exactly, I am not sure. It looks to be maybe about a half, maybe, and then over here it's a little less than a half, like a third or something like that. But we don't want to just guess. So we are going to hit second trace, which is that first step, right? Second trace. And then I'm going to hit 2 because I want to find the zeros. And then I got to go to my left bound. So I'm going to look for this one right here first, the negative one. So I'm going to arrow to the left, and we're going to see a little guy. There it is. So I got to go to the left of that point, that 0. So I'm going to go, I'm to the left now. I'm above it and to the left. That might be backwards the way I'm looking at it. I'm going to hit enter, and then I'm going to go to the right. I could have hit enter on the previous one, but what you see is these two arrows. It's hard to see this one, but they're pointing in towards each other at that 0. And then we want to guess. So I'm going to get kind of close to it, hit enter, and look at that. We've got negative 0.50. Okay, so we got negative 0.5, negative 1/2. And then we got to find the other one. So let me bring that calculator back up. So we're going to do the same process, but over here. Second calc, I'm going to go for option number 2. and I'm going to get my left bound first. So now I'm going to be under that 0 once we come around here and I see it. There it is. I'll hit enter. I'm to the left. See how it's pointing in towards the 0. I'm going to hit enter, and then we can either arrow back or we can just hit enter a third time there, and I get 0.3 repeating, which we know is 1/3. Okay, so x equals 1/3, and I'm going to make this negative 1/2 here, just so we're in fraction form for both. Wonderful. So this is a quartic function, right? A degree of 4, so it should have 4 solutions. We only saw 2 of them. So what we're going to do here is, I mean, who knows? It could have been coming back down somewhere else and we just didn't see it. But I think we got enough. We can really take care of this from here. So what we're going to do is we're going to do a bit of synthetic division now, right? That's our next step. Use synthetic division to get it to a linear or quadratic function that's left over there, right? But remember, it's all still a quartic function. We're just going to analyze that smaller part. Alrighty, so let's set up some synthetic division, and we got to be real careful here with fractions to make sure we don't mess it up. All right, so I'm going to have negative 1/2 in the box, and then I'll have 6, 1, 29, 5, and negative 5. I didn't have any missing terms. I don't like that 9. There we go. I don't have any missing terms, so I didn't need to put any zeros for placeholders. Alrighty, let's keep it going. So I'm going to drop the 6, and then 1/2 times 6, negative 1/2, that's going to be negative 3. We're going to add these, and I get negative 2. Multiply, I get positive 1. Add, I get 30. Multiply, I get negative 15. Add, I get negative 10. Multiply, I get positive 5, and then I get a remainder of 0. That should be the case, remember. I should have 0 as my remainder because this is one of my roots here. I'm dividing it out, right? X plus 1/2 is a factor. Alrighty. Now, I'm going to do synthetic division again. How about I change colors to showcase the second time? And I'm just going to set it up right here. Why rewrite the numbers? So, drop the 6. And I end up with 1/3 times 6 is 2. Add them, I get 0. That's going to be 0. That's 30 when I add. Times 1/3 is 10. And add and get 0. Once again, I should get a remainder of 0 in this situation. If you don't, you've done something wrong, either in your synthetic division or you didn't calculate it correctly on the calculator. Hopefully you did that step correctly and didn't make a mistake, but that's another thing you could go back and check. So now what I have is I have a quadratic left over that we can deal with. So let's see here. We've got 6x squared plus 0x minus 30 that we have left over. All right, and I want to point out that our function that we're dealing with right now is still the negative 1/2 would be 2x plus 1 as a factor. The 1/3 would be 3x minus 1 as a factor. And then we have this 6x squared minus 30, right? This is still the function. It's not like this is gone right here. We're just focusing on that part now to figure out the complex zeros, the imaginary solutions that we're going to have. So what can I do with this quadratic? Well, I can go ahead and set it equal to 0, and I'm going to do that. So I can solve this one. I'm going to add 30. Why did I put minus 30? That should be plus 30. Whoops. So I'm going to subtract 30, and then I'm going to divide by 6. I was looking at that there. I'm like, hold up. I'm supposed to have a negative over here when I'm in the square root. So I'm thinking ahead. I'm like, did I make a mistake? That happens, people. You make mistakes. So make sure that you are you're double checking things. You got to double check yourself before you wreck yourself, you know? All right, so I've got x squared equals, well, negative 30 divided by 6 is negative 5. Square root both sides. And I'm going to get x equals plus or minus I root 5. So those are my two remaining. Lovely. And these are imaginary solutions, which are included in the complex solutions as well. So, right, our reals and our imaginary are part of the complex. We jotted that down earlier. All right. So at this point in time, guys, I know the video is getting kind of long. I'm going to pause it and go over this problem here. So I'm going to hit pause. I'm just going to write it out and kind of stop step by step. So if you want to, we'll go through it quicker, but you can try this one on your own now. See if you got it. All right. All right, so I did my synthetic division with the two zeros that I found there. We had negative 2 across that, and at 1/3. So we were able to see this one and not have to use those calculator keys. But this one I did need to find that 0 using those steps. All right, so I'm left with 3x squared plus 27, and I'm going to set that equal to 0 like we did before. So I have 3x squared equals negative 27, divide by 3, and I get x squared equals negative 9. So I'll get x equals, after I square root both sides, plus or minus 3i. Bibbity bop, just don't stop. Nice work, you guys. I know that one got to be a bit long, but it's a bit of a lot of steps going on with these types of problems. So be very careful, especially when you're dealing with the fractions and synthetic division. It's easy to mess that up. Take your time. Always remember that you should be getting a remainder of 0. That's a great way to check yourself. And also, you should be trying to get some imaginary solutions here. So make sure that you don't make a mistake like I almost did that I caught in the previous problem where I accidentally threw a negative for whatever reason. All right? Always checking your work. Have a wonderful day. Make good choices. Keep it real. Keep it fresh. Always remember to do your best. America, freedom, rock and roll. And Costco.